Hi everyone, and welcome to this 6 i2X first season 2 meeting. And my name is Julia Matevosyan. I'm a chief engineer and associate director at Energy Systems Integration Group, and I usually lead this forum. So let me share my screen with a few intro notes. Lisa, can you please confirm that you can see my screen?
Yes, we can see the virtual meetings code of conduct.
Yes, it's not the first page. Oh. All right. So now I'm on the first slide. All right, so as I mentioned, we're now at the 6th meeting of the Forum for Implementation of Reliability Standards. Just so you know, the first half of the meeting will be recorded and maybe posted on the ESIG website. If you do not wish for your voice to be recorded or your video to be there, so please don't turn it on. And if you speak during the call, it is presumed that you consent to recording your voice and image. So just some goals and outcomes that are expected from this i2X first forum. The forum is conducted to facilitate understanding and adoption of new and recently updated standards that are relevant for integration of new generation resources. The forum convenes industry stakeholders to enable practical and harmonized implementation of these interconnection standards. In addition to these meetings, the leadership team produces a summary of meetings capturing recommended best practices, challenges, and gaps that require future work. So if you missed any previous meetings, please go to our website, and I'll have a link in a minute, and check the summary of the previous meetings, as well as recordings and slides. So just a few words about the leadership team. We have Cynthia Bothwell from Boston Government Services, contractor to DOE, Robert Reedy from Lindo Reed, contractor to DOE, Will Gorman from Lawrence Berkeley National Lab, Jens Boemer from Electric Power Research Institute, myself from ESIG, and Ryan Quint from Elevate Energy Consulting. So just a summary of the last meeting. So the last meeting was focused on IBR plant modeling and requirements and best practices. As always, I've given meeting introductions, and then Bruno Leonardi from New York ISO presented their perspective on IBR plant modeling requirements. There were some recent changes there. Then Kasun Samaras Sekera from Elevate Energy Consulting talked about IBR plant modeling and developer perspective, developer/consultant's perspective. And then Andrew Isaacs and Lucas Unruh from Electronics kind of summarized it. What's the latest about IBR modeling and where do we go from here? Some of the key themes from the last meeting. New York ISO is advancing the IBR modeling framework to align with Fork Order 901, New York State Reliability Council's Rule B5, and NERC guidances. And in that, they're trying to balance model fidelity with timely project delivery, as well as reliability and resource adequacy needs. EMT studies are becoming standards, and they are also increasingly so iterative, with screening tools being applied in the beginning of the interconnection process, and then identifying projects that are needing deeper analysis through EMT. And this analysis is conducted throughout development stages of the project and before commercial operation date. Real-world mismatches between models and equipment behavior highlight the need for standardized commissioning-based verification. And also we need consistent as left model updates. So as any updates are happening in the field after commissioning, those need to find its way into the models. Efforts like IEEE 2800 2022 and DLL real code wrappers and proposed .ibr mapping files, they all aim to improve consistency, traceability, and automation across OEMs and projects. So again, helping to capture any of the changes that are happening in the field post-commissioning. And then in the future, we need broader automation. We need improved modeling of power plant controllers and communication delay modeling, and as well as advanced screening tools for weak grid conditions and subsynchronous oscillation risks to enhance reliability, but also reduce dependence on a few experts that are available on these topics today. So just about kind of where we are on the schedule of meetings, we are here on October 21st, and we'll be talking about challenges of IEEE 2800 in 2022, and then planned revisions. And then the next meeting in November, we'll talk about change of management and how to handle it during IBR planned interconnection process, commissioning, and also how to maintain conformity throughout all of these changes. So again, here on the slide, you see the link to where all materials are posted, and it's currently also in the chat. All right, so for today's agenda, as I mentioned, we'll talk about some challenges with IEEE 2800 2022, planned revisions, and kind of other future plans with the standards efforts. So I'm almost done with my introductions, and then you'll hear from Andy Hoke from NREL providing an update on IEEE P2800.2 efforts. Then Manish Patel from Silicon Ranch will talk about potential areas and issues for forthcoming IEEE P2800 revision. And then Jens Boemer from EPRI will talk about forthcoming IEEE project authorizations, including new grid forming IBR recommended practices project authorization. And then, as always, we'll have presenter Q&A. So we'll use Slido to ask questions to presenters, and then we'll have structured discussion around the questions and topics of the presentations. So stay engaged and stay connected. Before we go to the presentations, I just wanted to bring to your attention these two trainings that are relevant to i2X first focus. So this will happen in November and December 2025, and you can see the links to both trainings currently in the chat. The first training is ESIG training on interconnection studies. It's a short course focused on best practices for performing study work necessary to interconnect inverter-based resources. The training modules will focus on expected day-to-day needs of engineers performing interconnection studies, model quality assessment, and inverter-based resource modeling and simulation work. So the idea with this training was basically for new practicing engineers that are just starting in this area to understand what are the main, main pain points, main concerns, and what to watch out for as you are doing interconnection studies for inverter-based resources. This training is hosted at Nextera's offices, and we would like to thank them for providing offices, and that allows us to keep the registration costs down. The second training is combined UE i2X and ESIG EMT training. So this is again 3-day in-person training to enhance knowledge and ability on performing EMT simulations. The training participants will learn practical methods and best practices that can be leveraged to enhance study practices across the industry. We'll focus again on expected day-to-day needs for engineers that are starting to perform EMT analysis and how they should manage EMT modeling and study practices in their organizations. This training is again in person and hosted by Texas reliability entity. So this one is in Austin in December. And again, thank you so much for Texas RE for hosting us. So yeah, if you're interested in these trainings, just please go ahead and register. As I said, we're trying to keep the cost of this training really down to sheer logistics because we have two hosts to provide facilities for us. Right, so without any further ado, there are code of conduct here, some rules that we hope you all follow. Please use Slido at slido.com and enter first 6 as an event code. And Lacey, could you please put that in the chat? Thank you so much. So use Slido for questions to the presenters, and we'll have Q&A after we heard from all the 3 of them. And without any further ado, Andy, I turn it over to you.
Thanks, Julia. Let's see here. Get my screen up here. All right. Everyone can hear me all right? So like Julia said, I'll talk a little about what's going on in IEEE 2800 land, especially 2800.2, the conformity assessment procedures for how we know if an inverter-based resource is following the rules established by 2800. And I'll talk a little bit about where we are and some of the recent developments there in 2800.2. So, like everybody else here, I'm just talking on behalf of myself, not on behalf of anybody else or any other organization. All right, so this is all old news to most of you, if not all of you, but just to sort of set the general background. In 2022, we published IEEE 2800, which established the first, what you could call, I guess, national or maybe international in a North American sense, standards for interconnection requirements for inverter-based resources, solar and wind and batteries connected to transmission and subtransmission. These mostly apply at the plant level. So far, they've been adapted by probably a couple dozen utilities and ISOs in bits and pieces. And they've also been, at least most of the ride-through aspects of 2800 have been incorporated into NERC PRC 29. Manish will point out some ways in which those are not perfectly aligned, but the general idea is that they're basically the same. So we have this interconnection requirement that was established in 2022. People are starting to adopt it. Some plants are starting to be required to comply with it. How do we know if we comply? In the interim, people are just using whatever procedures they can come up with, which is a perfectly reasonable approach. In the meantime, we've been developing for the past few years IEEE 2800.2, which is a recommended practice with conformity assessment procedures for IEEE 2800. We're currently in balloting. I'll talk a little bit about the details of how the ballot's going. I would say it's going pretty well, although we still have some work to do there. And we hope to actually finish around the end of this year and publish it early next year. So it'll be good to get that out the door. And then I won't talk too much about future stuff because Jens is going to talk about that. But we do have additional plans in the 2800 series for new standards, including some standards related to grid forming and a revision of 2800 to potentially fix some of the various bits and pieces that have been hurdles for folks that you've probably heard about in this forum, and that Manish will also talk about a little bit more today. All right, so that's the big picture. Why are we doing all this? I think you probably already are aware of this, but since 2016, people, or maybe even earlier, we've been trying to raise the bar on performance and modeling for inverter-based resources so that we can have lots of them on the system and still have a reliable system. They're being deployed. We need to make sure the system stays reliable as we deploy them. And so as we start to raise the bar on performance and require more modeling and these kind of things, how high and how fast do we raise the bar, right? If we raise the bar too fast, we'll end up not being able to interconnect because there's just too many, it's too difficult. We've gone too far beyond where industry was. So a lot of what we're doing right now is trying to find that compromise between how much can we raise the bar and get a more reliable system without necessarily putting a burden so high that it makes it too difficult to interconnect a plant. That's kind of the general paradigm, in my mind at least, as we develop these standards. And you've seen this slide probably dozens of times, but just to remind everybody, 2800 is a plant level standard. Most of the requirements of 2800 apply at the point of measurement or they can also be moved to the point of interconnection. So basically they're plant level requirements for the most part, with a couple of small exceptions. That's important to keep in mind because it motivates how one writes conformity assessment procedures. You've probably seen this slide before from me or from others, but what's in 2800.2, the conformity assessment procedures, is not just, say, stick an inverter in a lab and test it. It's a whole series of processes, because if you just stick that inverter in the lab and test it, you aren't necessarily going to know how the plant it's in is going to perform. So instead, the lab testing piece is just to validate the models. Then you build up a plant level model. You do some simulations on that model to understand how the plant's going to perform, ideally before the plant is actually turned on. Then you have the plant built. You make sure you actually built what you designed. You run some commissioning tests to the limited extent that you can in a commissioning test to understand how well the plant is going to perform. And then you again validate the model against those commissioning tests, and then also monitor the plant's performance in the field. So that's sort of 2800.2 in a nutshell. None of these things are going to be new wheels that we're inventing, right? These are also just collections of sort of best practices that a lot of folks in industry are already doing to some degree or other. So that's basically what 2800.2 is. I'm not going to go through all the details in this slide, but just to make clear, I'm the chair of .2, but it's a big leadership team of like 20 people, and even more beyond that are contributing in a heavy way. So just to basically say there's a lot of folks involved in this, and we'd love to have you involved too. There's a pretty big working group, over 170 voting members representing all pieces of industry. So we're pretty happy with the balance of the working group, that we're not balanced, that we're not sort of dominated by any particular stakeholder group. We've got utilities, we've got manufacturers, we've got regulators, consultants, IBR developers, ISOs, et cetera. So it's great to have that balanced working group. The ballot group is also fairly well balanced. There are 231 people signed up to ballot it. So it's great to see that high level of interest, and they're again pretty well balanced across stakeholder groups. All right, we had our first ballot in May and June of this year, and we actually did pretty well. We got an 87% approval rate, which exceeds the 75% threshold to pass. We also got enough votes returned. That's sometimes the harder part too, is making sure that everyone returns their votes. But we also got 743 comments from those balloters and another 35 public comments. And so for the past few months since June, that's what we've been working on, is resolving all those comments. We have to go through every comment one by one and say, okay, does it make sense to make some changes in response to this comment? If we're going to make some changes, what's the change? We basically just finished that last week. And just last night, I clicked the button to say, let's start the new ballot. It still is going through the process, but that will start maybe today or tomorrow. So that's sort of the next step, is finishing up this ballot. It'll probably take a couple more rounds just because of the way that the IEEE Standards Association procedures work. If you look at those 700 and something comments and divide them up by the sort of a topic, you'll see a whole lot of them are on the type testing piece, which is again this testing of a single inverter or turbine or power plant controller to make sure that its performance matches its model. There's also, to some degree, some checking of its performance capabilities in that type testing, but the primary purpose is to make sure that the model matches it. And then, as we talked about, the design evaluation comes next, where you evaluate the whole plant design and make sure the plant as a whole conforms with 2800. So those are the two groups, the type testing and the design evaluation, that got most of the comments. There were a handful of comments in other areas on the commissioning and as built, a handful on power quality, and there's actually a frequency scanning group. So actually, we haven't talked too much about this, and maybe some others have in this forum, but as part of type testing, there's frequency scanning that goes on to make sure that the dynamic aspects of the model match the dynamic aspects of the hardware. So anyway, you can see the hot topics there were type testing and design evaluation. I'll just summarize a couple of the themes from comments, and then I'll move on, let you folks move on to the next presenter. So one of the big debates in the comments and in the working group as a whole throughout the whole development process was, how prescriptive do we want to be? Do we want to tell you exactly how you run every test, and by doing so, maybe make things more standardized, and that might make things smoother because every plant's doing the same thing. You sort of learn that process and you can be more efficient about it. So prescriptiveness is one aspect, but there's also a balance with flexibility. Some of the working group members would prefer to leave most of the tests fairly general or fairly vague even, because it gives you the flexibility to deal with the fact that not every plant is the same, not every system you're connecting to is the same, and you need some flexibility to be able to tweak the procedures to fit the specific application. So that's the balance we've been trying to strike the whole time, and there's some pretty strong opinions on both sides. Overall, when we went from the previous draft 3.2, to the draft that will be released like tomorrow probably, draft 4, it's a little bit more prescriptive. Some of the tests have a little bit more detail, but it's still pretty general and flexible. And it's still a recommended practice, right? It's saying here's a recommendation on how to check conformity of the plant, not here's the way you have to do it. Of course, we all know sometimes some user of the standard might pick up a certain piece of it and say, we're doing it this way, and now you have to do it that way because the authority governing the interconnection requirements said so. Anyway, that's one theme, is this slightly more tilt towards prescriptiveness, but still pretty general in 2800.2 draft 4. You can see that in the type test. There are more details in some of those type tests now. There's more tables and test profiles than there used to be, but not to a huge degree, just slightly more specific, I would say. And there's also a little bit more rigor for frequency and Rokoff ride-through testing. We kind of came to this conclusion that these things are pretty hard to test in a commissioning test. They're pretty hard to test in the field. And so the time to try and make sure that at least the inverter can ride through a frequency or a rate of change of frequency event is in the lab. So there's a little bit more rigorous checking of that now in the type test. There's a whole bunch of other changes, but that's sort of the two that jumped out as me is worth calling out. When we get to the design evaluation, the modeling and simulation, again, we're trying to deal there with this question of how high do we raise the bar? I would say the overall trend going from draft 3.2 to draft 4 was to actually lower the bar just a little bit. For example, we took out quantitative IBR unit model validation. In other words, like, is it plus 5%, plus or minus 5%? When you're trying to match a simulation trace to a model, to a hardware test trace, or is it some other number? We had a framework for that. That's actually gone now. Now it's all left up to qualitative. Basically, just an engineer looks at the traces and says, looks good to me. It is the paradigm there. That's actually not that huge of a shift because the quantitative framework was always kind of a suggestion and was never really fully complete, but it's not even in there at all anymore. So that's maybe a to-do list for other work. There was also some discussion of to what extent do we need to require or suggest the use of non-aggregated models that have, say, every inverter or turbine represented, or maybe every feeder at least represented inside of the plant. That content was moved to an annex, so it's sort of a little bit less of a high bar there in terms of how often non-aggregated models would be used. And then there was some discussion about what sort of test system to use. Do we want to use a simple test system or a more detailed test system that represents the real grid where the IBR will be connected? That choice is still in there, and it's basically left up to the user to pick which of those makes sense for each case. Commissioning tests, I would say, went in a similar direction to the type tests, where there's somewhat more specificity now. We added specific tests, for example, for voltage feedback, reactive power control, and power factor control that weren't in there before. Those, I guess we should point out, are only required, or also, well, the best way to say it is probably they're not required if the plant will never operate in the particular mode that would be tested, right? You only run the test for the modes that the plant would operate in. That, again, is something we could debate. There are some people who would say, no, we should run all the tests. We want every plant to be capable in case we need it in the future, but that's not the way the standard is going. There was also some requests to say align the standard with specific regulatory frameworks. We in general decline those requests and try to just keep it general. All right, I think that's about all I wanted to say. I mentioned already timeline-wise, we're hoping to finish up the balloting and recirculation late this year and publish early next year, which leaves, I guess, the next step for others to think about, and Manish and Jens can talk about that. Thanks, everybody.
All right, thank you, Andy. Just a reminder to everyone to submit your questions on Slido with event code first6, and you can see the notes about this in the chat. And with that, we move on to Manish. You already heard from Andy that some of the challenges were identified during IEEE P2800.2 process with regards to what in 2800 may need revision going forward. And so that's something that Manish will talk about next. Go ahead, Manish.
All right, thank you, Julia. Thank you, Andy. So 15 minutes or so on some areas or issues to consider in the next revision of the standard. I tell you, this is not the only list, right? I think if you want to get a true list, you have to, go with me for a drink and you get the true list. This is the version for 15-minute presentation, right? All right, with that said, whatever I say today are my own personal views. They don't represent the working group or standards association or my employer by any means. Simply Manish Patel trying to put two and two together to understand what the standard means. All right, why am I? Let's try this. Okay, I think Andy had this picture in his slide, but I think it's very important that we understand this. Most of the requirements of the standard apply at the point of measurement. That's the default reference point of applicability in the standard. This is, in simple words, high side terminals of the main IBR transformer. Then there's a short tie line and then a point of interconnection. Very few requirements in the standard apply at the point of coupling. Few days ago, I thought only fault current injection requirements applied at the point of connection and directly on the terminals of the IBR unit. I think someone brought to my attention that there is something else in the standard that applies to IBR unit, and that is something that we might want to clarify in the next revision, but we'll talk about that in a second. All right, so first one, reactive power capability requirements. This is clause 5.1 in the standard. The default reference point of applicability is point of measurement, so this is the plant level requirement. Very simple illustration here with two figures from the standard. ICR is the IBR continuous rating, so if it's a 100 megawatt plant, then ICR is 100 megawatt. What this means is that for any active power between 0 and ICR, the plant is required to be able to absorb and inject 33% of ICR as reactive power. So x-axis is megawatts or active power, y-axis is reactive power. Now, in case of type 3 wind turbine generators, we recognize there is a limitation. So when the active power output falls below 10%, the reactive power capability is reduced by this slope line. But in simple words, the plant is required to provide 33% of the ICR otherwise for whole range of active power output from the plant. The figure on the right is for plants that are able to absorb active power from the system, so battery energy storage, for example. In this case, ICAR is the IBR's continuous absorption rating in watts active power, and then reactive power capability is on the y-axis. Same as the other side of the slide here, 33% of ICAR, both absorbing and injecting. So that's what the standard requires. Somewhere in that clause, and this is what I mentioned earlier that someone brought this to my attention, it says that IBR unit shall have the capability to provide reactive power when primary energy source is available and not available. So this is to emphasize that, say, the sun went down, primary energy source is not available. If it's a solar plant, then the plant or the units in the plant shall have capability to provide reactive power, right? The second statement again emphasizes IBR units shall have the capability to remain in service while not exporting or importing active power except for importation of active power to cover losses. Anyhow, I think this should be IBR plant and not IBR unit, but we'll let the next working group to take care of it. But this is something that needs clarification. If you have a 100 megawatt plant, for example, with 20 solar inverters in there, then I don't think we need to have all 20 inverters to be able to provide reactive power, because if this is a plant level requirement where you only need to provide 33 megawatts absorbing or injecting when active power output is 0, one could easily do that with just handful out of 20 inverters. So it is important that this gets clarified in the next revision of the standard. All right, so the previous two figures that you saw were active power versus reactive power. Pretty simple. Well, for what voltage does that relationship apply? So then that is specified with this figure and a lot of words to go along with it. What this means is when the voltage is greater than V4, so if you come down in this table and look at the V4 ranges, they're usually high, 105% all the way to 110%, right? So when the voltage is fairly high on the system, there is no need for the plant to operate at 0 reactive power output. When the voltage is high, practically you would like that plant to absorb reactive power from the system, help reduce the voltage on the system, right? So that's why you see this dashed line that goes from V4 to V5 all the way to 33% requirement. But anyhow, what this means is when the voltage is high, we don't need plant to be capable to absorb, operate at 0 reactive power output. So then if you apply the same rationale and come on the other side of the figure where the voltage is less than 95%, all the way down to 90%, because there is no slanted line like this up here, what this means is the plant shall be capable to operate at 0 reactive power output when voltage is less than 95%. Anyhow, just engineers thinking here, what could be the system scenario where the plant needs to operate at 0 reactive power output when the voltage is less than 95%? They would want plant to inject reactive power into the system so that it helps boost the voltage above 95%. So anyway, something to think about for the next working group revising this standard. All right, so then clause 5.2 states that the plant shall have capability to operate exclusively in following control modes. One is RPA voltage control mode, another one is power factor control mode, the third one is constant reactive power control mode. So today I'm only going to talk about this voltage control mode option. I do have some thoughts on power factor and reactive power control mode also. But in respect of time, just the voltage control mode. So this is the language in a voltage control clause 522. It says the IBR plant shall operate in closed loop automatic voltage control to regulate the steady state voltage at the RPA to the reference value as adjusted by Drup function to within 1% of RPA voltage set point. I'll stop right there. All I want to say, and you have to go back and think about this, maybe look up some control block diagrams, try to put 2 and 2 together. I think the use of terminology, reference value, and voltage set point may have caused some confusion. So we need to make sure that in the next revision, this is all clarified. Also, depending on Drup and pre-event reactive power output, regulating voltage to within 1% of RPA voltage set point may not be possible. I think the intent here may be that regulate the voltage to within 1% of the reference value adjusted by Drup function. But anyhow, I don't want to offer solutions. I might not be right anyway. Just want to state that the use of terminology has caused some confusion, and maybe this is all clarified in the next revision. The second one here is the standard clearly states that the voltage control system shall be capable of reactive power Drup. I have seen some transmission entities require voltage Drup instead of reactive power Drup. So maybe the standard should, in next revision, allow that option as well, instead of limiting to reactive power droop control only. All right, so then this has also gotten some attention in the industry. When you're doing voltage control, the standard goes into performance requirements. It states that the reaction time shall be less than 200 milliseconds. Step response time could be anywhere between 1 second and 30 seconds, and this is usually specified by the transmission entity, and the damping ratio of 0.3 or better, right? So then when we think about how to meet this reaction time requirement of less than 200 milliseconds, this is all we need to think about. There is a voltage at the point, there is a meter at the point of measurement that usually measures the voltage. It sends that voltage to the power plant controller, so there is a communication time between the meter and the PPC. When PPC does get the new voltage from the meter, there is a little bit of time delay before it actually recognizes the change in the voltage, and then it issues new command to IBR units. There is a extensive communication network between PPC and all the IBR units in the plant, so there is some communication delay there. And then at the end, once IBR units get a new command from the PPC and reacts to it, there is a bit of time delay in there. So all those need to be such that the reaction time requirement of less than 200 milliseconds could be met, right? One more caveat, if you go and look at the reaction time definition itself in the standard, it says the duration from a step change in system quantity measured. I highlight the word measured. So does that mean that the time that meter at the POM takes to measure the voltage is not part of this reaction time? I don't know what the right or wrong answer is, or I don't want to imply that I know the right or the wrong answer, but I think there is an opportunity to clarify all this. All I could say is that it is my recollection that when the 200 millisecond number was agreed upon within the working group, it included the measurement time for POM voltage. That same thing applies. There is another requirement in the standard for fault current injection, which has a step response time. And there also, the time that we agreed in the standard included time for measurement and a change of a control quantity, right? So anyhow, we need to make sure this is all kind of cleared up in the next revision. All right, write through. IBRs have to write through. I agree. I think it does not make sense for IBRs to go offline for a pre-cycle fault on the system. But I think this write-through word is so powerful, and I personally feel that we missed the boat a little bit in understanding what we mean by write-through requirements. So in the standard, you will see a figure like this in the annex, a table like this in the main body of the standard. The standard goes on to explaining there are three possible interpretations of this table and a figure. And standard tries to convey that the correct interpretation or understanding is that this is voltage versus time curve. For a given voltage, IBR plant shall not trip until the duration at this voltage exceeds write-through curve capability. This is definitely not voltage deviation multiplied by time as an area integration, right? This is not voltage versus time envelope so that you can have actual event, say, recorded by a DFR. You take that trace, you overlay it on top of this curve and decide if the plant was able to write through or not, right? So standard goes and tries to clarify all this. It is then the interpretation, at least in my mind, that if you had a single voltage disturbance event, where voltage drops from nominal to zero at 160 millisecond to 25%, at 1.2 second to 50%, and hugs the boundary of this LVRT, then the IBR is required to write through. That is okay if that's the correct interpretation. I think it's very important that we understand this so that when we type test the equipment, we type test it correctly. When we run simulations on the models, we run those simulations correctly, right? All right, so then PRC 29 came along a little while ago. A lot of words here on the screen. I'm not going to read English and try to understand it, but there is attachment 1, item number 7, that kind of clarifies what is the meaning of voltage right-through in PRC 29. And then in IEEE 2800, there is this statement in clause 7221 that clarifies what is the interpretation of voltage right-through. I think both of them mean something different. So if you have a hypothetical event like this, voltage drops from nominal to 60% at 0 time, back to 80% at 2 seconds, and back to nominal at 3.5 seconds. Plant is allowed to trip for IEEE 2800, but not for PRC 29, right? So again, look, I don't think I want to say what is right or wrong. I don't want to get into a debate where we discuss the interpretation of this English language, right? What I'm trying to say is it's very easy to say in concept, we want IBRs to write through. I agree with that. It's very difficult to write exactly what that means. And if we want this thing to be done consistently in future, it is very important that we get this cloud cleared up, right? All right. Transient over voltage right through requirements. You all might have heard this. This is clause 723. This has been nightmare of my life, I guess. I was in charge when we were trying to come up with this requirements when the 2800 was written. Again, the default RPA is POM. The standard says that IBR plant shall write through transient over voltage that do not exceed the fundamental frequency over voltage right through requirements in 7221 and rest of the things. So let's pause right there. It says standard is required to write through transient that do not exceed the fundamental frequency of voltage right through requirements. If you read this again and again and again, I think I heard this from someone else, and then it started to make sense. My interpretation is that transient voltage right through requirement is an exception to fundamental frequency voltage right through requirement. For example, fundamental frequency voltage right through, right? It uses, in simple words, RMS voltage. You could have a RMS voltage at 1.05, but for a very short duration over one cycle, the voltage went up to 1.72. Your RMS voltage does not change a whole lot because for the rest of that full cycle, the voltage was back to normal. So if the voltage went above 1.7 for more than 0.2 millisecond, then even though the voltage remained within the continuous operation region or mandatory operation region, the plant is allowed to trip, right? So I don't think many people get this, but it's an interpretation that transient voltage right through requirement is actually an exception to fundamental frequency voltage right through requirement. Second, I mentioned this already, the requirements apply at the point of measurement. Typically, there is no transient voltage protection at the POM. That kind of protection belongs in the controls of IBA units. So one has to understand how to reflect any transient that appears at the POM of this magnitude for this duration, and how it would appear at the POC. Do we do this analysis using aggregated models? Do we do this using non-aggregated models? Again, and this is a cumulative time over a 1 minute time window. This times are in millisecond. So 15 millisecond is less than one cycle, right? And this is cumulative over 1 minute window. So a lot more cycles. So how would you even measure that in real world? So anyhow, I think the intent of the requirement is clear. We need IBS to write through transient voltage but how to write a requirement, how to test it, how to show conformance remains a challenge, right? All right. The last one here, consecutive voltage deviation right-through capability. This is clause 7224. This is second nightmare of my life. Again, I was in charge. It says IBR plant shall write through multiple excursions outside of continuous operating region with following exceptions. And look, I'm not going to read all this exception, but I'm going to go back and forth on those two slides for a second. Okay, this is one set of exceptions that you see on the screen, and then there are four more. 4 or 5 here, 4 more here. When you start reading those exceptions and start understanding that for anything that is not within this exception plan needs to write through, there could be hundreds of scenarios. How do we show conformance during study work? How do we show conformance during type testing? How do we show conformance in actual real world events? So again, the intent was pretty good. We want IBRs to write through to the extent possible multiple voltage dips in a short duration of time. It just becomes very difficult to write something in plain English that is clear and not ambiguous, right? So this is another opportunity to get it all sorted out. All right, so consideration of energy displacement during fault and post-fault active power recovery. I feel we could have written not only consecutive voltage dip, but we could have written even voltage write-through requirement that was somehow tied up to energy displacement. Because I don't think this is only an issue during consecutive voltage deviations. It might also be a real thing for some IBRs, if not all, some type of IBRs, even for one voltage dip that is of extended duration, right? So a very simple example here, this is offshore wind plant, for example, connected to the transmission system via HVDC line. In this case, typically, there's a big DC chopper onshore on the DC side of this DC to AC converter station. And this chopper is usually designed to absorb 100% rating megawatts or active power, 100% of active power rating for 2 seconds, right? So depending on K factor used in this DC chopper, I mean, in this DC to AC converter station, for a 50% voltage drop, say K factor of 2, 100% reactive current, that means any active power that gets dumped into this HVDC line cannot go out because this converter station is pumping out reactive current. That means all that active power goes into a DC chopper. But that DC chopper can only absorb all that active power for up to 2 seconds only. After that, there is a mandatory cooling time and all that stuff. That can then be extended. What is the active power recovery time? Is it 1 second, 2 seconds, 5 seconds? Depending on the active power recovery time, this DC chopper is, for example, absorbing power, right? So all this needs to be thought through. Maybe in next revision of the standard, we understand the energy displacement a little bit better, what IBRs are able to absorb in terms of energy displacement, not, and then write up some voltage right through and consecutive voltage dip requirements accordingly. And with that said, this is my last slide. The person here in the middle, IBR, is me. This is my typical day. I work for a solar developer. I work with a lot of utilities in Southeast. There are NERC requirements, there are IEEE requirements. All they say one thing, OEM on the other side say another thing. Somehow trying to make all that work is quite a fun. With that, Julia, I'll hand it back to you.
Thank you, Manish. And I really love your art there. So it's funny. All right, so we now move on to Jens, and he'll talk about forthcoming revisions of 2800 and how do we fix all the issues that Manish was just talking about. Go ahead, Jens.
Yeah, thank you so much, Julia. Thank you, Andy, for your overview. And Manish, I'm trying to pitch here to the group to get engaged in the next revision. And now I worry that people are concerned that they might have nightmares from their standards development. Now, that's just like joking. It's actually a lot of fun writing these standards. I would encourage everyone to already start thinking ahead how to get involved. I just put a link into the chat window. Maybe somebody can put that also onto Slido, where you can register your interest if you're not already a member of the respective working groups. But anyhow, I'm going to give an overview on the forthcoming revision of IEEE 2800 and also the development of a new IEEE Recommended Practice for grid forming equipment. A few standard disclaimers here. I'm talking on behalf of myself. I am not talking on behalf of any of our EPRI funders, and EPRI does not give regulatory advice, but we can be helpful with understanding and interpreting standards. I'm also not representing the IEEE Standards Association, and any IEEE standard is a voluntary standard. Now, that becomes more relevant or is different once IEEE standards get adopted. But so far, the adoption is at an entity-by-entity basis and not at a national level at this point. And last not least, some of this work is supported by the US government, but I'm not talking on behalf of them. So I'm changing slide templates here because I'm going to give you an introduction into the IEEE, Power and Energy Society, Energy Deployment, Power Generation, Wind and Solar Power Plant Interconnection and Design Subcommittee. That's a mouthful. So this is a subcommittee that resides under the EDP&G committee in the PS Society of the IEEE. And the scope of this subcommittee, which is also the main sponsor for IEEE 2800 and 2800.2 and any of the forthcoming projects, is that this is the subcommittee that deals with all interconnection and design matters related to the grid integration and delivery of transmission and distribution connected wind and solar resources. It provides a liaison to and cooperates with other committees, subcommittees, working groups, task forces, including standards making groups in IEEE and other organizations with similar interest. Areas of interest include best practices, engineering design, safety and protection related issues, technologies related to interconnection, and also standards, recommended practices, and application guide development, including education. So this is a subcommittee under which the working group that is developing these standards is housed. And you can go to the website and see more information. You can look at some past meeting minutes and announcements for future meetings. And it also includes a link to a website where you have on one page all the forthcoming projects under the working group. The subcommittee has more than one working group. The working group that is the home for IEEE 2800 and 2800.2, which are the only published standards in the 2800 or in development standards series, is the Inverter-Based Resources Interconnection Working Group, or IBRI working group. We also have a second working group, which is the Wind and Solar Power Plant Collector Design Working Group. And they actually published a guide, two guides, 2760 and 2778, which may be a little bit less known in the industry compared to 2800, but nevertheless quite useful guidance for how to design and plan grounding systems in wind and solar plants. And one of them is also being updated right now. So if you are already engaged in what used to be called the IEEE 2800.2 working group, then you do not have to do anything. Now this working group has been renamed to IBRI working group. But if you are not part of that yet, I encourage you to either follow the direct link that I copied into the chat or go into IEEE My Project and find the menu where you can manage your profile and interests, then go to interests and add a group, find the inverter-based resources interconnection group, and declare your affiliation. That way you will make sure that you stay up to date on the existing and any of the forthcoming projects. Now, some people may ask, okay, why does it not already show those forthcoming projects that we will elaborate on here now? The reason is that those projects are not yet authorized. Once they have been approved by IEEE, which we expect to happen later this year, they will also show up in the list under the IBRI working group. So here comes the update on those forthcoming projects. We started out by asking the various stakeholders and subgroup leaders and working group leaders that are involved in the 2800 and 2800.2 working groups, and also had discussions at the PS general meeting and at a recent subcommittee meeting. What do you actually need? What do you expect from this next revision cycle of IEEE 2800? And what we heard was that there are three important items. One is people are seeing more and more grid forming technology entering the grid, and technology providers providing such inverters that can operate in grid forming mode. And so there were some concerns raised that parts of IEEE 2800 may be overly specific and could potentially create a technological barrier towards this grid forming performance. So a desire was expressed to reduce those barriers to the extent possible. And that is one scope that will be conducted under a very succinct narrow scope amendment, 2800A. Second, industry stakeholders expressed the desire to specify optional grid forming equipment level capability and standardized performance. And that's a project that is being proposed to be a recommended practice in a 2800.1 project. And third, as you have heard from Manish, stakeholders have identified significant opportunities to revise and improve this first version of IEEE 2800 based on industry learnings collected during the adoption process. And that's a project that can be executed under P2800 once approved by IEEE. Now, one of the challenges is how to keep all of this consistent, how to integrate the grid forming into the 2800 series, how to make sure that if a potentially grid forming barrier is removed, that this does not then degrade the reliability requirements from 2800 itself, and how to keep all of that in balance is quite a challenge. And therefore, the proposal is that anything related to the grid forming amendment and also recommended practice development would be conducted by the same group of subject matter experts, which then also would have to coordinate that with those with the working group that actually developed and will revise IEEE 2800 as the main standard. That way, things can stay coordinated, and we can avoid as much inconsistencies as possible. Now, to make it even more fun, there's also an attempt to coordinate the grid forming equipment level recommended practice with the IEC as a potentially joint project towards an international standard and dual logo IEEE standard. Now, for those of you less familiar with the differences between the IEEE documents, a standard documents mandatory requirements, all in the context of voluntary industry standards, and uses shall language. Examples include IEEE 2800, but also 1547 and 1547.1. The recommended practice documents are documents in which procedures and positions preferred by the IEEE are presented. So you may have a list, and among that list, there may be one preferred way or method. And 2800.2 is such a recommended practice, and the grid forming 2800.1 would also be at a recommended practice level. And then you have guides, which are documents that furnish information, provide alternative approaches for good practice, and suggestions stated, but no clear-cut recommendations are made. And those use may language, whereas a recommended practice uses a should language. So here's an overview, including some of the timing of these forthcoming standards. 2800A and 2800.1, which are related to grid forming, would be developed over the next year throughout 2026. And then the projected date for submitting these standards to the REFCOM of IEEE would be early 2027 for a possibly April 2028 publication date. But that would require that the initial ballot of these two projects starts in late 2026. So the idea is to turn around this grid forming related scope fairly quickly. And that could be done in a task force that is housed below the IBR interconnection working group. Compared to that, the revision is currently proposed to be on a little bit of a slower cycle. It can also start in the same time, sometime early next year, along with the work on these other two projects for grid forming. But the expected date to initiate ballot might be more or less around March 2028. And then the publication date may be more in the April 2029 area. Now, those colors used on this slide just indicate in red what is a standard, and in blue what is a recommended practice, in order to differentiate the level of mandatory requirements between 2800A and .1. And 2800.1 would be a project that we will try to coordinate jointly with IEC. As I said, the EDPG Wind and Solar Power Plant Interconnection Design Subcommittee is the main sponsor. But as we have done in IEEE 2800 and also 2800.2, we are hoping to have co-sponsors support this project and this series of projects, including committees like the Transmission and Distribution Committee, the analytic methods for power systems, power system relaying committee, and SC21, which are responsible for the IEEE 1547 standards. And those committees have confirmed their joint sponsorship, and other committees may further support, because the scope of 2800 itself and its subsequent documents does cut across various scopes of those other committees. Now, here's one more tidbit about how we envision the development of these different projects. As we said, they would all be housed under the same working group, but the grid forming projects could be developed within a grid forming task force that would be formed under the working group. And all three documents, the main standard, the .2 and the .1, they would be developed by pretty much the same people, with subgroups that are based on topical areas, for example, the general requirements, the reactive power and voltage control, the active power frequency, or the response to abnormal conditions. Those subgroups would cut across each of those documents, so that if, for example, a change is made in the base standard related to reactive power, one of those examples that Manish offered, then the idea is that those changes would also be considered in a future revision of 2800.2 for the test and verification procedures and pass-fail criteria, as well as any potential changes that relate to the grid forming requirements, and so on and so on. This is a new way of developing these standards, so we'll all have to see whether it gives us more nightmares or less, but hopefully it will at least increase the consistency between the base standard and its sub-projects. Now, one question is related to the grid forming standard, how that can actually become complementary to IEEE 2800. Because to some extent, IEEE 2800 may already stretch into performance requirements that are related to grid forming equipment. But there's still this gap, and the new project is meant to fill the gap from whatever 2800 right now provides in order to increase the share of inverter-based resources all the way to true grid forming capability, which the working group will have to figure out what that actually means. And I will not go into the detail here, but the next two slides illustrate how these three documents could interrelate to each other. On the left, we have a potential list of areas where technical barriers exist in 2800 and could be looked at in order to remove them under the amendment project. In the middle, in blue, we have a list of potential functional capabilities related to grid forming to be specified in the .1 recommended practice. And on the right, we have the list of potential revisions related to 2800 based on industry learnings. And one idea is that the future revision, which runs on a little bit of a longer timeline compared to the development of the .1 grid forming recommended practice, could then include references to some of these grid forming requirements as optional requirements, or using should language to make that link from the next version of 2800 into the 2800.1 recommended practice. Now, coming closer here to the end of my presentation, we're also trying to coordinate this grid forming recommended practice with the IEC. One of their challenges is that they currently do not have a interconnection standard like IEEE 2800 in their system. So they may be starting out with a technical specification that is currently focused on distributed energy resources. That would be the first scope for them to translate some of the 2800 into that context. A second scope would be to focus on grid forming equipment level framework requirements, which then can provide the framework for technology-specific grid forming requirements within other technical committees of the IEC. And a third scope would then expand their plant level requirements to cover the full scope of 2800. And last not least, the fourth scope would expand that plant level requirement to also include the grid forming. Now, this is all international standardization, so I will not bother you too much with this, but the idea is that we want to coordinate to the extent possible the grid forming project with IEC. Now, what does that all mean for the adoption of 2800 now? First of all, you can continue adopting IEEE 2800-2022, for example, with a hybrid integration approach that also addresses some of those known deficiencies in the first edition of the standard. But we would highly encourage all of you who have or are adopting IEEE 2800 to then also get involved in the next revision cycle, so where you can bring your learnings back to improving the standard, which would start sometime next year. Second, once the next revision is available, a detailed reference and customization approach can be used, because that would allow for more of a partial adoption and more consistency. But maybe not all gaps will have been addressed in that next revision. But the recommended practice for grid forming equipment may then be available and could also be referred to. And we do expect that after the next revision, there will be a subsequent revision. And hopefully in the third revision, we all have a standard that has closed gaps and is consistent. So maybe later on, entities can move towards a general specification, which is the most harmonized and coordinate way of adopting a standard like IEEE 2800. So keep adopting it and get engaged now. And to wrap this up, we have some related EPRI offerings, including a tool that can help assess conformity with IEEE 2800. And we are launching a collaborative forum that can complement this i2X first forum and other industry forums with deeper technical EPRI-related collaboration. We are going to have a preview call for that tomorrow. Some of you may have received that invitation. Others can reach out to me if you have not and still want to participate. And with that, I'll hand it back to you, Julia. Thank you so much.
Great. Thank you so much, Jens. So now we'll spend maybe 15 minutes or so, 20 on the Q&A. And I've seen some questions got answered in the chat, but in Slido. But I think I want to ask or like voice them anyway to get answered.